Notice my quick sketch of the tangent function. Now it's just a sketch. Remember, I'm not looking for specific solutions, but I am going to kind of trim this down a little bit. I'm just going to focus on the part of this graph on this interval from 0 to 2 pi. So I know tangent begins at 0, and the period of pi splits apart here. Halfway through that period, we have our first asymptote. Pi away, we have our next asymptote. That would be 3 pi over 2. And because the period is pi, 0, 1 pi, 2 pi, there we go. This is the portion that we're going to look at from 0 to 2 pi. How many solutions does this equation have? Well, this equation is talking about tangent. That's why I graphed it. And I'm seeking to understand which angles, x would be an angle, which angles have tangent ratios of negative 0.35. I bet there's a couple. Well, how many? That's what we're doing now is we're counting. So tangent is unbounded, but there are those nice moments at the pi over 4s where we have tangent ratios of 1 and negative 1. We'll be looking at the negative side of things here. So I think right about here would be our first solution on this interval, with a negative 0.35 ratio, and I believe, I'm pretty confident it would happen once more. So here we have two solutions. All I'm doing is counting them. I'm not finding them precisely. Two solutions on the interval. What about this function? We have 2 cosine of x, and in the equation format here, we're looking at 2 cosine of x being equal to 1. So the cosine function is what I'm going to graph. Amplified by 2, scalar of 2, cosine, cosine, here you are. But again, we're just looking on an interval. So from 0 to 2 pi, there we go. This is the portion of the wave that I'm looking at. How many times or how many solutions will we have where the output is 1? Well, it happens here. I'm not going to be able to find that angle at this moment, but it happens here and here. I'm counting 2 solutions once more. Is it always going to be that easy? Of course not. Let's try one with a very different type of period. To the best of my drawing abilities here, I'm working on this problem now. Sine of 20x equals 1/3. On this interval, negative pi to pi, I will ask the question, how many solutions? Not seeking the exact solution, so I just want to know how many there are. I'm going to visualize, and then I'm just remembering I said, hey, let's do this graphically and analytically. We'll do it another way in a second. So here's our sine graph, roughly. Notice I'm not using a calculator. Maybe you can't tell. I'm not using a calculator. This is a hand-drawn graph. I'm going to figure out the period and then label a little bit of this to start to generalize. The period is no longer 2 pi. This function has been horizontally shrunk by a factor of 1/20th, which means the period is now pi 20ths. Nope, how about pi tenths? Pi tenths, that sounds better. So if we start at 0, we get back to 0 a second time here in that tiny fraction of time, pi tenths. This would be 2 pi tenths. This would be 3 pi tenths, and on and on and on. How many solutions do we have where we actually equal 1/3? This is a bounded function, remember, so it won't go higher than 1. Let's say 1/3 probably occurs right about there. 1, 2 times in a period, several times actually. By the time I get out to pi, and I'm not going to waste my time trying to draw this whole darn thing. Instead, I'm going to generalize. So in this first pi tenths, 1/10 of pi, we saw 2 solutions. So if I extend this thinking in pi units, like 10 tenths of pi, we should have 20 solutions. And that would just be on the interval from 0 to pi. Our interval here goes from negative pi to positive pi, not so clearly drawn by you, Mrs. D. But this is a symmetric function. we would probably see the same number of solutions. Yep, every period there would be 2 solutions there. So we're going to double this 20 and conclude there are 40 solutions on that interval. Now you could enter this into your calculator, but it would probably show up like this, and that's kind of hard to see, hard to count, so my hand drawing I feel like is sufficient. In this problem, we're going to shift gears. We're actually going to stop graphing maybe and look for analytical route. Because here we're not just looking for counting the solutions, we want to find them. We want to find all of them. Notice this problem is not presented on an interval. We are finding like an infinite number of solutions probably. So here goes some analytical work called algebra. I'm going to work with this equation but maintain the equality. And we have 5 sine of x equals 1. Sine of x will equal 1/5. That's not a ratio I'm familiar with. It's not a special angle, but we're trying to solve for x and angle, actually a whole bunch of angles. This equation has infinite solutions. Here I'm going to take a picture of the unit circle for myself, and I'm going to say, okay, pi over 6 has a sine ratio of 1/2. So I'm guessing this angle x is something that's smaller than pi over 6. I could get a specific value here. I'll use my calculator, and I'll say, hey calculator, which angle has a sine ratio of 1/5? That's the inverse sine function. We'll get that number, but let's talk about all the other solutions, because of course I could continue rotating around the circle, terminating in the same position. That angle, that acute x angle, is a solution. But there's a second solution that would be coming from quadrant 2, some obtuse measure with the same reference. This would not be x degrees or x radians. This would be 180 minus x. From this x-axis, we're going backwards x degrees. That would measure this obtuse angle. So that's it. Those are kind of the 2 terminal positions. Again, I could rotate around and around, forward or backwards. In either of those terminating positions, and the sine ratio would be 1/5. So I'm going to grab my calculator and get this positive x angle. My calculator is reporting to me that that acute angle is 0.2014 radians. I'm in radian mode, and that's kind of the mode that we're going to be in for the rest of this course, radians, unless given in degrees. But here we are finding the angles. We'll find them in radians. This angle, then, I'm going to have to do pi minus that, and I get 2.9402 radians. Unfortunately, there are only 2 answers listed here for x, and I need to generalize at this moment. I need to say, hey, I want all of these answers reported forever. So all of the coterminal angles with angle x could be found by saying 0.2014 plus or minus in either direction 2 pi n. The other solutions for x would be stated by the starting point of 2.402 radians, again adding or subtracting 2 pi n. This generalization talks to me about coterminal angles. It also gives me solutions forever and ever in both directions. Solutions for x, again, this angle x is measured in radians. One last note about generalizing. If we're generalizing solutions, and let's say you have a nice angle, because you will get some nice problems, say that's pi over 3. You find that x equals pi over 3 is a solution. You also find that x equals, 4 pi over 3 is a solution. If you want to state these solutions forever, there's no need to go all the way around the circle. There is a nice clear connection between these angles. They are collinear, meaning they're only 180 degrees apart, or pi radians. So we could generalize if we were finding x here with some tangent ratio, right? Tangent would be the same value here as it is here. I could write the statement or the recipe here that x is the angle pi over 3 plus or minus pi n, and that would cover not only these angles terminating in quadrant 1, but also these angles terminating in quadrant 3. So the general statement for all solutions can be expressed sometimes by adding 2 pi, sometimes by adding pi. Visualize with your unit circle here and you can get a good idea. You can also think about the period of the function if you're doing it graphically rather than analytically. Good luck with your homework practice. Think smarter, not harder, whenever you can. Mrs. D signing out.